Okay, finished.
The first one is finished?
Yeah.
That's nice. You can start doing the next one if you like.
Yeah.
I will wait a bit and like solve this for everyone, if that's good.
Yeah, that's my thought. Give me one more minute.
Yeah, that looks good. You BFS, right?
Huh?
BFS, right?
Yeah.
That's nice. This probably needs BFS.
I will challenge you another problem if you would like.
Another problem?
Yeah. I will give you another problem if you want to challenge us.
Yeah, you can do that. But I'm not sure if I will be able to do it right now. You can give it that to me. That's good.
Yeah.
I don't prepare that much. This. To replies to like the discussion things. That's easy. Other than that, project or intro to software engineering. Then project one for theoretical computer science.
What is your account? I will send you this problem.
What is mine? this problem. I haven't, let's see. I will, let me give me a moment. So here,
I'm wicked, you know.
3 states, right?
I'm wicked.
3 states.
I'm done.
Completed this one? That's good. All right. So this problem is pretty easy. You can use breadth first search for this problem. Basically, this is a map, and the idea is to like start from maybe from any point, but you can like start from the start here. So you start here, it's a wall. It won't happen, right? So you move like this, then like this, and when you come here, you see like this is the floor, right? So when it's a floor, we immediately mark it as visited. So this is visited, and also add it to the queue here. So this is 1 1. So 1 1 is added to the queue, and we repeat the process every single time by using BFS. So this is also another one. So we mark it like this, and this creates a cell, right? This creates a cell because there are no other ways. So that's one. You can also so using BFS, you can also count the number of like after using BFS, you can also count the number of rooms at the same time. So this constitutes one room. And then when you use the loop again, you arrive here, and you can use BFS here again. So this market as visited, then you maybe, I don't know like what my algorithm follows, but like you can go here, then you can go here, you can go here. These are all the cells that you can go. Yeah. Was this like this? I don't remember. Yeah. So this also constitutes one of those cells. Wait, did I make a mistake here? 1, 2, 3. No. 4. This one should be, no, this one is this. So these three, and these. So except this entire section constitutes another room, and the same can be said for this too. Since you solved this, I won't delve too deep into the solution. Maybe we can move to the next problem. You can see my solution there too, but yeah. For the time complexity, it's going to be approximately of n times n, because at most we're visiting every single cell exactly once, right? So that constitutes to O of n times n, because we also have visited. So like if the cell is visited, we are not visiting it again. That's basically the algorithm for this one. We can move to the next problem. Go here. Go a bit down. Yeah. So this is a solution for it. You can, since you completed this, I don't think you need this. This is the next problem. You find park, that like the second link. Yeah. This is the second problem. So I can describe the problem here pretty basically. So you start from a point from the root node. I would say like the root node is like his house, and basically like this person wants to celebrate his first big salary by going to a restaurant, and he lives in an unusual park. The park is a rooted tree with n vertices, and the root at vertex 1. The root is his house probably, and yeah, it's his house. And unfortunately, the park also contains cats, and he has also already found out that there are what are the vertices with cats with them. So I can kind of explain the algorithm. So it has a few things. I will write it down. So basically, they mention that it's a rooted tree, right? It's a rooted tree. Which also means that there will be no cycles in this problem. Like if it's a rooted tree, then for n edges, for n vertices, it will be exactly n minus 1 edges. And the vertices are from 1 to n. inclusive. And they mentioned that the first vertex, which is 1, is the house of Kifa. So this is his house. And they also mentioned that each path has a certain number of cats, right? So a certain number of cats, let's say that's M. When you, and the problem also mentions at the end, so the leaf vertices of the park contain restaurants, and Kifa wants to choose a restaurant where he will go, but unfortunately he's very afraid of cats. So there is no way he will go to the restaurant if the path from the restaurant to his house contains more than M consecutive vertices with cats. So basically, since this is a tree, I can show you like an example of what this means. Think of it like this. I'm not going to draw it completely, but think of it like this. This is a tree, right? This is the root node. It basically means that you need to basically go through all the paths and make sure to compute the total number of paths that has no more than M consecutive cats in there. So this can be a cat, right? This can be a cat. And if M was, let's say, 2, you won't be able to, so I think it's no more than, right? So if it contains more than that, so like if you see like the number of cats getting 3, the consecutive cats getting 3, you can't like traverse this path because Kefa is too afraid to go down this path. And take this as a leaf node, right? So this represents the restaurant, right? This is like the main algorithm here. I'm not going to go too deep, but like this is the main flow of it. You are given a tree with the vertices and edges, and the weights represent if it has a cat or not. I will go in detail after that, but basically this node, let's say this one, right? So your task would be to compute all the paths. Let's say this is a path, right? This is a path. This is a path that contains no more than M consecutive cats. What does M consecutive cats mean? If for example, if a path, let's say this is a root node, right? If a path contains, let's say, two cats, and M is set to 1 here, they mentioned that M is like M has to be like no more than like the number of consecutive cats has to be no more than M, right? So in this path, the consecutive number of like cats is 2, which is like exceeding 1, right? So this path is invalid. You can't go through this path. But what about something like this? Let's say this was not the case. This was, let's say, another node. You go down here, there is another cat here. You go down here, and let's say this is the restaurant now. What would happen in this case? Will he be able to go down this path to the restaurant? M is still 1 here. Consecutive cats mean like if the cats are like consecutive, if they're like together, like in a single like cycle, right? So in this case, you start at 1, you go to this cell, there's a cat. Number of cats is 1 now. You go to, I would say like I should increase this to 2 to make it even better. You go to 2, number of cats is 2, M is 2 here, but it's still valid because like it isn't like greater than M. So like 2 isn't like greater than 2, right? So it's still valid. And then we go to this cell. This cell doesn't have a cat, so you can visit this cell, but the number of consecutive cats will now go to 0 again. Then you come here, you see 1 cat again. Consecutive cats, 1. And then you reach the restaurant, the leaf node. Like, is it understandable? Like, or maybe am I like making it too complicated here?
I can understand.
All right. I will give you some time to review the problem. What's time now? 11:55, right? Maybe like 20 minutes for this problem to, yeah. Do I need to use a variant of Dijkstra's in this problem?
Direction.
Dijkstra in this problem for shortest.
You can use, but it is not optimal.
It's not optimal, right?
You must use the one that is more advanced in the chart for this one.
It's an interesting problem. Are you solving this one right now? Or
Huh?
which one are you solving right now?
What?
Which one are you solving right now?
What is
Like, which one are you solving right now?
I don't understand.
Like, which one are you solving right now?
This one?
Oh, this one? That's nice.
Because I still get a book.
Oh, that's nice. Good.
But I think I feel it's not. So I will solve the problem that I sent you.
This is an interesting problem.
Okay, I printed the 2-1. So I saw the thing that I read here. I wonder why it is so.
Empty.
Yeah.
I don't even know why I just saw empty. Do we know why I saw empty? Yeah. I don't know. Last time there were like many people.
May I ask a little bit? You are in Arizona, right?
What?
You are resident here?
Nah. I'm international student.
Huh?
International. International.
International?
Yeah.
Okay.
People look at this. I guess, another 4 minutes. Do you need some more time, or like should I go with solution right now? Do you need some more time, or should I like solve it right now?
Huh?
Do you need some more time for this problem?
Actually, I finished 10 minutes ago.
10
I'm
minutes?
working on my problem.
Oh, that's all right. All right. This is also a good problem, I would say. So since you solved it, I will kind of go through it, go over it maybe. So the first problem, I think, n vertices. So I guess each of them connect to 1 and 3. So something like this. This is node 1. This is node 2. This is node 3. And this is node 4, right? And they also mention like which one of them has gas. Now I forgot what does 1 and 0 mean here. They mentioned that somewhere. Yeah, one means it has a cat. So this has a cat, and the second one has a cat. So an M here is what, 1? M here is 1, right? So you need to maintain 2 things in this problem, or actually I say like 3 things. First is like have a track of the total number of consecutive cats, like total consecutive cats. Second would be to early prune prune from the tree or the path if the cats, like total number of consecutive cats exceed m. So early prune. And the third would be to use DFS in this problem. DFS. So the core DFS algorithm for this problem is like you basically, when you reach the leaf node, you just like return 1. And that's my approach for this problem. Return 1, but for every single other nodes, you basically return like 0. Like it basically means something like that. So if the leaf nodes will return 1, but like these nodes will like represent 0. Like not return 0, but like represent 0, basically. These will like represent 0. So any other node like that, just a dot leaf, it will represent 0, and like the leaf nodes will represent 1. Now, now you need to also maintain the consecutive total number of cats, right? So for this path, let's say you start at 1, right? This is a house of, I don't forget the name of that person. So you started here, right? So here when you go to this path, consecutive cats become 2. So you immediately stop and return back to 1. You backtrack again to 1, right? You immediately stop and backtrack to 1. And in this case, when you see that the path is like not correct, at that case, you will immediately return 0 here. So you return 0 here. You go back here and you go down this path. Now this path is a leaf node, so it will be 0 plus 1, which is 1. That's one solution here. You backtrack again to 1, you come back again to 1, now you go to this path. In this path, it's again 1, right? So like it's a leaf node. So you will do, so this will be again 1. So basically you will do 0, 1 plus 1, which is 2. I think the answer is 2 for this problem, right? It's 2. So I know like this might look a bit confusing, but like if you know recursion, you can kind of like get the idea of this problem, like how to kind of formulate the early pruning strategies here so that you don't go to the entire tree at once. The time complexity of this would be approximately O of n because there are n vertices and n minus 1 edges. So n plus n minus 1 would be approximately like O of n plus n minus 1 would be approximately O of n, like still, right? So time complexity would be approximately O of n plus n minus 1, which is O of n. Space complexity should also be O of n. In this case, yeah. So I can show you my algorithm for this problem too, but it's there. Could you go back to the? I'll go a bit down. This is, yeah. So yeah, I basically used this algorithm. So it might be a bit long because I'm not that good at like writing C++ code yet. But yeah, this is the algorithm for this problem. You can see through. But since you guys solved it, so I don't think you need to see the solution for this one. But yeah, it's available on this website. It's my portfolio website. You can find the links there. It should be in the logs section. You can find like in the navbar in the logs section. You can find all the contents of the ICPC primer section that we are doing here. So if you like want to maybe revisit some concepts from last session that we have, they are there. So you can find them there too. The video that I used for last session is also available on ACM's YouTube channel. So I think you guys will be able to see that, right? ACM's YouTube channel. Yeah, like they're in the ACM YouTube channel. So I think we are off already. Yeah, I only had like planned 2 problems for this session. I didn't give much thought about this. But yeah, good work. Thank you so much. If you guys have any questions, feel free to let me know. I have a question for you. So for that problem that you showed me there, uh, do you like need to maybe compute like the point where all the three dots, like all the three like states connect?
I don't understand.
Like there are like three states for that problem, right? So like 1, 2, 3.
Yeah.
So do you like need to like for all the roads, do you need to like find the point where like every three like every three states connect, something like that?
Yeah, you might find the point that between them, and it can be the tree. Like, for example, the one here, the two here, the three here,
Yeah.
then you will find a point in the middle, connect three of them together.
Yeah.
And so that you want this, the distance between this one and this one plus this one to this one plus this one to this one is the sorted. And then if you wanna find a sorted path between two nodes, you can use the extra one.
The extra one, yeah.
But you should consider this one because in this graph, so that you have two situations, right?
Yeah.
So if the two things connected together
Then
and they are identical, the weight of the weight between the weight of the edge between them is 0.
Yeah.
But if they are different, for example, this one and this one,
Yeah.
so the weight between them is 1. So you must use the concept named BF01.
Yeah, BFS01, you're right.
And then, yeah, so it will help your problem run faster than the digital. Actually, you can use the digital for this one, but
like
can
this
be
doesn't
slow.
need the extra in this case. It's faster for like using this approach. I kind of understand.
Yeah, of course, because that is BS. So that's why you should use this one. And here is the code.
This is really good. Like I need to solve this problem by myself first, but like I kind of get the idea for this problem.
Yeah.
This is nice. This is a nice problem.
So that's a solution.
You're right. All right. Do you guys have any other questions? That's good. That's good. You can stay here. We have the room booked till for like 3 p.m. or like how much?
3 or 4.
3 or 4, right?
Yeah.
That's good. So after this, probably from 1 p.m. I think. Do we have lunch? I doubt it. So like I think we don't have lunch today. So basically what happens is like after 1 p.m. the ICPC primer session ends. And from 1 to 2, we usually have like lunch break. And after that, one of the other guys from ACM will host their own session for the ACM art session, where like they go over like one of the research papers, like one of like research papers related to like LLMs and all those stuff.
Yeah, I'm attending.
Yeah, you might attend that. That's nice. So I think you might have to wait for some time. It will start, I think, at 2 p.m. right? Yeah, you're right, at 2. So yeah.
Lunchtime 1 to 2, where there will be networking and lunch and social.
Yeah, so I don't think we are gonna have lunch today, but like we can have, but like I don't know, like I don't think we are gonna have lunch today. Because like
so the lunch and session is not lunch and social session is not happening.
Yeah.
1 to 2.
So you can stay in this room like till that, like for that time, but you can go home too. Like it's up to you.
What?
Like that's not happening. I think so because like it's not happening. It's not happening.
It's not happening.
No.
I want to do.
Yeah.
Because too little people to mix around.
Yeah, you're right. So I think after that,
then I'll go off and just come back to.
You can do that. You can do that. You can do that.
But even the research, the 2 to 4 section, right? Because I attended a similar research discussion.
That's all right. So I think
over Zoom. So I'm wondering 2 to 4 is also can tell over Zoom, right?
2 to 4 can also be on Zoom. You're right. 2 to 4 will be also on Zoom,
it's
right?
Entirely more of just like the previous. There was a recent research discussion, I think, shared by one of the ASU researcher. So it's similar to that. like just share using the PowerPoint.
It's
Then
similar
I
to
will
that.
just attend from Zoom.
That's all right. That's all right. So you can attend that from Zoom too. So that's it then. I think we are done. Are you gonna stay here?
Me, yeah.
For the entire